Alright, so let's start again. So welcome back. I hope you guys had a great break, and I hope that you watched the 3 or 4 lectures that I asked you to watch. I'm actually going to put them on the YouTube playlist. I'm going to intersperse the older lectures from about 3 years ago that I asked you to watch. But I think we're not going to be using what I did in those lectures. They're closely related to this stuff, but they were an application of Moebius function and Moebius inversion to the theory of hyperplane arrangements. But so what I wanted to do today is discuss the Moebius function a little bit more carefully and Moebius inversion in a few more examples. Okay. So first of all, just to remind you, the Moebius function of a poset was a function of 2 variables, x and y. Okay. And I don't know, let me just draw some random poset here. Like that one maybe. And so just to remind you quickly how this goes. So for example, if we want to compute mu of the bottom element comma something. Okay. So remember what we do. Let me write them in blue. So you put a 1 in the bottom element, and then for each element, you look at the ones below it in the poset, and I mean less than or equal in the poset. Sorry, I mean less than in the poset strictly. And the idea is that with this one, they should add to 0. Okay? In other words, if you look less than or equal to there, those numbers should add up to 0. So less than or equal to here, this plus this should be 0, so I get a minus 1. This plus this should be 0, minus 1. This plus this should be 0, minus 1. Now for this one, I should have this plus this plus this plus this is 0, so this is a 1. This plus this plus this plus this is 0, so this is a 1. Now here, this plus this plus this should be 0, so I get a 0. And finally here, the sum of all of them should be 0, so therefore I get a 0. And so these blue numbers that I drew are only the numbers mu of 0, comma x for the various x in the poset. And if you wanted to do mu of, let's say, a comma something, then you would do this same procedure, but starting at a and going up. Okay? And so here what I wrote is just, again, the definition of the Moebius function. Again, so the idea is, in the poset from x to z, you look at the Moebius from the bottom of the poset to all the elements of the poset, of the interval from x to z. From the bottom of the interval to all the elements in the interval from x to z, and the sum should be equal to 0. Unless x and z are the same, the interval is trivial, and mu of x comma x is always equal to 1. Okay? And then we wrote down the Moebius inversion formula. The Moebius inversion formula is about functions that map the poset to the integers. Okay? Or it doesn't even have to be the integers. The poset to any, I guess, any abelian group where you can add things. Okay? And so the idea is that if your function g is obtained from your function f by saying g of t is looking at all the elements below t and adding their f values, then f can be obtained in the same way from g. The only difference is that you have to put the Moebius function in between. Okay? And so this gives you some kind of alternating sum expression for f in terms of g. Okay.
Federico?
Yep.
Question about your example.
Mm-hmm.
When you said that one is less than it, do you mean by, I guess, pictorially a ranking procedure or a tiered procedure, or the ones that are directly connected to that?
So remember that when I say less than or equal in the poset, it's not about the ranks, it's about who is less than it in the poset. Okay? So like in this case, I put a 0 because the ones less than in the poset are this one and this one.
Okay.
But not these other ones, because even though they're lower, they're not less than this one in the poset.
Okay, so why is the top one 0? Because it's not greater than that one.
Well, that's a really good point, actually. Yeah, so you're right. So when I look at, I did this wrong. Thank you. This one, I should look at the elements below it in the poset. But this guy is not less than this one in the poset. All the other ones are. Right? So therefore, I guess the value here should be 1, so that this plus this plus this plus this plus this plus this is 0. Okay. So what I wanted to do today is discuss some examples of this Moebius business. And let me start by proving a lemma. So let me prove it over here. Because the first example that I want to discuss is a very simple example. It's an example that I discussed in the lectures that you were supposed to watch. So for the Boolean poset, right? So we saw in the lecture videos that the Boolean poset, if you look at the Moebius function, it's just ones and minus ones. 1 minus 1, 1 minus 1, 1 minus 1. And I gave a proof there, but I want to give a proof that's maybe a bit shorter, more conceptual. So let me prove a lemma, which is that if P and Q are posets, then I would like to describe the Moebius function of the product P times Q. Okay. Now, so what's an interval in P times Q? Well, first of all, remember that the elements of P times Q are pairs of something in P and something in Q. So that's one element. And now I need to go to a bigger element. Right? Now this is less than this when P is less than or equal to P prime, when Q is less than or equal to Q prime. Right? That's when this is less than this in the product poset. And I want to show that Moebius functions are multiplicative. In other words, this is just the Moebius function of P, of P comma P prime, times the Moebius function of Q, at Q comma Q prime. Okay, so let me tell you that there's a couple of proofs of this, and depending on how much you like algebra, you can remember that mu actually we defined it before Thanksgiving. We defined it in terms of the incidence algebra of the poset. Right? And you can think of this as relating the incidence algebra of the poset of P times Q with respect to the incidence algebras of P and Q. Okay? And if you like this kind of thing, then you should prove that the incidence algebra of P times Q is actually the tensor product of these two incidence algebras. And if you prove that, this follows. But I know that some of you haven't taken the necessary abstract algebra for that argument. And actually, this is easy to prove just directly from the definitions, because all we have to do is verify this equation. So we need to take some interval, let's say from ST to S prime T prime, okay? And we need to verify that. Well, let me say it like this. I mean, what needs to hold is this property. This should be 0. Right? That's what I would need to show. I mean, sorry, it's not what I need to show. This is what holds, right? This is the definition of the Moebius function of the product. And what I want to do is that I'm just going to replace this stuff and prove that this expression satisfies this equation. And because this equation characterizes the Moebius function, that means that the Moebius function must be this. Okay. So let me take this thing and just compute S to P T to Q. Okay. And I need to prove that this is 0. But then we're summing over P and Q that satisfies it, right? And so this means that P has to be between S and S prime, and Q has to be between T and T prime. Okay? And then I have this thing. Actually, let me leave a little bit of space here. And now, this is a double sum, right? I'm summing over P and over Q separately. So let me put it here. Okay. And now the thing is that, you know, I have a product of two sums. This one and the other one, right? And this one. And we know that this is generally 0, right? I mean, the black sum is 0 unless S is equal to S prime, and the blue sum is 0 unless T is less than, unless T is equal to T prime. Okay? So this is 0 unless S is equal to S prime and T is equal to T prime, in which case it is equal to 1. Okay? And so that means that it's exactly this, right? Because S equals S prime T equals T prime is the same as saying that ST is equal to S prime T prime. So this verifies this formula. So that's a simple computation. I mean, it's kind of messy, but I really didn't do very much there. And the reason that I wanted to do this is that now I just want to remind myself that the Boolean poset is just a product of the poset of two elements a bunch of times. It's the product of the chain of two elements n times, where this is the poset of two elements, 0 and 1. Okay? And because I know the Moebius function of this one is very easy, then I'm going to get the Moebius function of the whole thing. Right? Well, first of all, what is this? So if I want to compute the Moebius function in the Boolean lattice from some set S to some set T, I want to use that this is a product of things like this. And what makes this explicit is to write this like this. I can think of S as being a 0, 1 vector. Where the ones are the positions of S, and the zeros are the things not in S, right? So I have a set, and I represent it as a 0, 1 vector. And then T is going to be some set that contains this one, right? And so that means that it's going to be some other vector, but it is important that whenever I have a 1 in S, I should also have a 1 in T. So, I don't know, let's say that this is equal to 0, 1, 0. Okay? And now, this really makes explicit that this is a, this makes this isomorphism explicit. Because now, I mean, I'm being a little bit lazy, but I should really make this a, with parentheses. This is a vector. And so this is the same thing as mu in the 2 poset of 0, 0, mu in the 2 poset of 1, 1, mu in the 2 poset of 0, 1, etc. Mu in the 2 poset of 1, 1. Okay. And what are these things? Well, what is mu in the 2 poset of p, q? Well, mu of 0, 0 is 1. Mu of 0, 1 is -1. And mu of 1, 1 is 1. Let me write it like this. Mu of 0, 0 is 1. Mu of 0, 1 is -1. And mu of 1, 1 is 1. So this is just a product of 1s and -1s, right? How many -1s do I have? The number of -1s is the number of times that I have a 0 here and a 1 here. Right? Here T is the collection of 1s. So the number of times that I have a 0 here and a 1 here is precisely the difference between T and S. So it's just -1 to the T minus S. And so that's a pretty nice, simple conceptual proof that the Moebius function is just 1s and -1s for the Boolean lattice. Okay. So that's that. And now let's think about what the Moebius inversion formula says here. So let's write this, but in terms of sets now. So I use capital letters for sets. Sum as the S subset of T of f of S. Right? For all T subsets of N. Okay. Yes?
Sorry, can you go back? What's in the dot, dot, dot? Like, what is that called?
Oh, so I mean, here I have one term for each. Now, this is this 0 and this 0, then this 1 and this 1.
Oh, I see.
This 0 and this 1. So I have one
For
term
every
for
slot.
each
Okay.
for each element of the vector. Okay, so Moebius inversion just says this, and so I'll just write it like this: f of t equals sum over the subsets of t of, now here I get g of s, right? But I have to put the Moebius function. But I know what the Moebius function is. The Moebius function is just -1 to the. Okay. And so this is familiar to us. This is exactly the inclusion-exclusion formula. So Moebius inversion for the Boolean lattice is exactly the same as inclusion-exclusion. So this is one way of thinking about Moebius inversion. It's something more general than inclusion-exclusion. Okay? For the simplest case, it gives us inclusion-exclusion. Okay? All right. So now, how about we do a different example? When my poset is the poset of divisors. And remember, for example, if n is 30, we did this picture, and it looks like this. We saw that basically these posets decompose as a bunch of chains. So here, this is 1, 2, and 4. This is 3, and this is 5. Okay, the 3 prime factors are 2, 3, and 5. And 2 appears. Can't. I guess I did 84, but 60 also works. And 60 is 2 to the 2 times 3 times 5. And, so, and this works for any integer, for any positive integer. You decompose it into its prime factors, and then each prime factor contributes a chain to this poset, and the product of those chains. So here's the chain from 1 to 2 to 4, here's the chain from 1 to 3, and here's the chain from 1 to 5. And in general, this is equal to the product of chains of size alpha 1 plus 1 up to alpha k plus 1, where n is p1 to the alpha 1, p2 to the alpha 2, to pk to the alpha k. And this is supposed to be boldface, right? So this is the chain of size alpha 1 plus 1. Okay. And I have alpha 1 plus 1 because this goes from 1 to the prime squared up to the prime to the alpha. Okay. So what is the isomorphism from Dn to this product? What it is that if you take a divisor, let's call it B, then you just figure out what the prime factorization of it is. Right? It has to contain at most the same primes because it's a divisor. And each one of these guys is less than or equal to alpha I. And so I map this to the vector beta 1 up to beta. So I just, for each divisor, I just say how many times does each prime appear. So, I don't know. We could take this one, for example. That's 4 times 5, which is 20. So 20 contains 4. It doesn't contain any 3s. And it contains a 5. So that's my map. Okay, so that means that if I want to find the Moebius function of this poset, well, I'm all set if I can find it for these posets, right? But that's actually very easy, because for these posets, if you look at a chain, in some chain, let's call it alpha, what is the Moebius function of s comma t? Well, what you do is that you say s is somewhere along the chain, and t is somewhere either at s or higher than s. And so, for example, if t is up here, then to compute mu of st, what I do is that I say mu of SS is 1, then for this one, it and the things below it should add up to 0, and so I get minus 1. For this one, it and the things below it should be 0, and so I get 0, 0, and I get 0, 0, 0 from there on. Right? In a chain, the Moebius function is very simple. 1 minus 1, zeros. Okay? So this is going to be equal to 1 if t is equal to s, minus 1 if t is equal to s plus 1, or 0 if t is greater than or equal to s plus 2. Okay? And so that means that if I want to compute the Moebius function, let's say from B to C. B and C are divisors of n. Okay. So then again I can think of this as a tuple. Okay. This is beta 1 up to beta k, comma, gamma 1 up to gamma k, where B is the product of pi to the beta I, and C is the product of pi to the gamma I. Okay. Now, this is a product, right? The Moebius function is multiplicative, and so I get the product from I equals 1 to k of the Moebius function in the chain alpha I plus 1, alpha I plus 1 of beta I to gamma I. Right? From beta 1 to gamma 1 I get a term, from beta 2 to gamma 2 I get a term, and so on. And so I get this product, okay? Which looks a little bit messy, but it's really not messy at all because, again, these things are just 1s, minus 1s, and zeros. Yeah?
Why do you need to specify which chain it's on by putting mu alpha I plus 1?
Yeah, so that's one good point, is that this is just kind of cumbersome notation. It is important because I need to specify what poset it's in. Right? Since dn is the product of these posets, then my formula tells me that the Moebius function of the product is the product of the Moebius functions of the posets. But I agree that it's pretty irrelevant what this alpha is. This just depends on beta I and gamma I. And so that's the next thing I'm going to say. Yeah. You can just think of it like this. Right? And so what is this thing? Well, it's a product of zeros, minus 1s, and 1s. Now when you multiply things, 0 is a pretty overbearing character, right? As soon as you have 1 0, it's gone. So if you happen to have one term that's equal to 0, this thing is just 0. Okay? So this is 0 if some gamma I is greater than or equal to beta I plus 2. Right? And if that doesn't happen, then you just get a bunch of minus 1s and 1s. And again, 1 is pretty irrelevant to multiplication, so you just care about the minus 1s. How many minus 1s do I get? I get minus 1 to the t, where there are or I should say where alpha I equals beta I plus 1 occurs t times. Okay. But let's think about this. This is otherwise. And by otherwise I mean this doesn't happen. But let's think about this a little bit more. So what does it mean to have gamma I greater than or equal to beta I plus 2? Okay, let me look at the number C over B. Okay? What ends up happening is that pi squared divides c over b. Right? Because the difference between the number of pi's in C and the number of pi's in B is at least 2. Okay? So this happens if pi squared divides C over B for some I. Okay? And what happens if no square divides C over B, then what do I have here? What I have here is that I have exactly T primes that divide C over B, where alpha, this means pi divides C over B. And so really, a nicer way to write this is just that I have 0 if some square divides C over B, and if that doesn't happen, so I'm going to just erase all of this stuff. 0 if some prime square divides C over B, and minus 1 to the t if C over B is a product of t primes. For some primes. Distinct. Okay. And one thing you'll notice is that this is completely independent of n. You don't see n at all in this formula, which is kind of what Brian was pointing out earlier. So actually I can just call this number mu of C over B. It just depends on C over B. And actually there is a function in number theory that is called the Moebius function. When I learned it, I thought, okay, well, what kind of definition is this? This is the strangest definition. Because they tell you, the Moebius function of a number is 0 if some square divides the number, or if the number is a product of primes, then you get minus 1 to the number of primes. Okay? There's always, when I learned this in number theory, I thought it was a very strange definition, very unmotivated. But this explains where that definition comes from. I mean, it's not the most beautiful definition, but it's a kind of inevitable definition if you want to do this enumeration of these kinds of posets. Okay? So that's the Moebius function from number theory. And actually, the next thing you learn in number theory is that there's something called the Moebius inversion formula. And that's nothing but the Moebius inversion in this poset. Okay, so this is the Moebius inversion from number theory. And it says, I mean, it's no surprise what it says. It says the same thing. If g of t is the sum over the divisors of t, f of s, that's true if and only if f of t is the sum over the divisors of t of the Moebius number of t over s times. Okay. And this is a function that really appears in many. Sorry, this is a formula that is very useful in several places in number theory. Okay. So that's it for the divisors of n. Now, let me just point out one more thing, which is the following. How can you tell, looking at the poset, if you're in this situation, or in this situation. In other words, looking at the poset of divisors of a number, how do you know if a square divides that number or not? Yeah?
It seems like if you're in the bottom case, everything underneath it would look like a cube.
That's exactly it. So you're in this situation where you have t primes that are kind of contributing different directions in the poset, and the interval from b to c is just a Boolean poset. So it's a cube of t dimensions. Okay. Whereas if you have some prime squared, then you have two edges going in the same direction like you do here. And your poset is not Boolean. Okay. So actually a different way of saying this is that this is 0 if the interval is not Boolean, and it is this if the interval is Boolean of size t. Let me now say that in a more general case. So what happens if we consider now another family of posets that we have studied is distributive lattices. So remember that this is the poset of order ideals of P. Okay? And you guys did this in one of the short homeworks very explicitly. And one thing you remember about these things is that they look very cubical. They're not a cube, but they kind of look like a stack of cubes, okay, of various dimensions. What is the Moebius function in one of these guys? It turns out that it's exactly given by the description that I just said here. So maybe the first thing I'll point out is that distributive lattices are not products. So this technique doesn't apply anymore. This technique actually doesn't work very often because most posets are not products. But still, these things kind of look cubical. So maybe you could hope that similar expressions hold, and it turns out that that's true. Okay? So it turns out that this is 0 if the interval from I to j is not Boolean. L, and it's equal to if your interval is Boolean, like this, then we know the Moebius function of a Boolean lattice, right? It's -1 to the t. So again, the Moebius function of a distributive lattice is very nice and simple, just zeros, ones, and -1s. Okay? And proof is not too hard. You can see it in the book, or you can actually. In the book, Stanley proves this after developing a little bit more theory, and then he gives a nice, short, slick proof. But you can also just kind of compute and prove that this is really how it works. Okay. All right. So that's the distributive lattices. And another family of posets that we have considered that's very, very important I mean, hopefully by now you're also getting the point that one thing that a combinatorialist does after finding a poset, when we discover a poset, one of the first things that we want to know is, what about the Moebius function? Can we compute it? And if we can compute it, and if it's nice, then we have Moebius inversion, and we have all these different enumerative consequences that are that we can follow. Okay. So what about for the partition lattice? So remember, the partition lattice is the lattice of partitions of a set where you go up by merging blocks. Okay. So I can either merge blocks 1 and 2, or 1 and 3, or 2 and 3. And then no matter where I merge, I'm going to end up with only one block. Okay. So this is the partition lattice I3. Okay. And we would like to find out what the Moebius function is. Okay. Now let me show you something. Because when we find the Moebius function, in principle, we have to do it for every interval. So what if we consider some interval, like, I don't know. So that's some partition. And now let's consider a partition that is higher than it, meaning that it's coarser, meaning that you merge blocks of this one to get the other one. Okay? So I don't know, let's say for example that we merge the blocks 1, 4, 3, 5, 7, and 8. Okay? So I merge this one, this one, this one, and this one. And there's no order in the blocks, so I shouldn't put the 4 before the 3. That looks strange. So that's the merge of these 4 blocks. And then let's say that I take these 2 and I merge them into another block. Okay, let's consider that interval. So think about it. You have 1, 4, 3, 5, 7, 8. And then you have 2 and 6, 9. Okay? And you want to merge, so if you want a partition that's in this interval, you want something that is coarser than this and finer than this. Right? So you're allowed to merge blocks, okay? But to be finer than this one, you can only merge blocks over here. You cannot merge 3, 5 with 2, right? In other words, what I'm doing is that the black partition is the left partition, and this green partition is this partition, right? So how do you get the partitions that are in between? Well, basically, you just merge things here as much as you want, and you merge things here as much as you want, but they don't interact with each other. Right? And so what you do is that you consider all the partitions of this set of 4 elements, consisting of 1, 4, 3, 5, 7, and 8. And then you merge these guys as much as you want. Okay. So this denotes the partitions of the set of 4 elements. So the elements are these blocks. They're just 4 things. Forget the labels, they're just 4 things. Okay. So this is the same as this, which is the same as pi 4 times pi 2. So the point that I'm trying to make here is that if you have any interval in the partition lattice, any interval, whether it's this one or any other one, any interval is a product of partition lattices. Okay. So, for example, if I want to find the Moebius function of this interval that I wrote there, by the product formula, it's just going to be the Moebius function of pi 4 from bottom to top times the Moebius function of pi 2 from bottom to top. Okay. So the point is that really we're just reducing to finding the Moebius function from the bottom to the top. If we know how to do that for any n, then we will know how to do it we will know the Moebius function of any interval of any partition lattice. Okay. So let's call mu n this number. So the point is that if we have mu n, then we have the whole partition, the whole Moebius function. If we have mu n for all n, then we have all these Moebius functions for all n. Okay? Okay, so let's do it for pi 3. So here, the Moebius function goes from the bottom to the top. So here it's 1, then here minus 1, minus 1, minus 1. And so here, it's 2. Right? So this is the first of these important examples where we get things that are not 0, 1, or minus 1. Okay? Okay, so what's 2? 2, it's a little bit hard to make a conjecture with this example. If you do the next one, you're going to find that it's, if you do pi 4, you're going to find that at the top you get a minus 6. And if you do the next one, you're going to find that it's 24. And then you can formulate a conjecture. Right? Turns out, where is my? So here's a fact. It's minus 1 to the, how much? Minus 1 to the minus 1 times and this is a very interesting result that, I mean, the formula is nice and simple, but the trouble is that we don't really know how to say, or we know how to prove things are equal to n minus 1 factorial by saying, well, you're just counting something. But the trouble is that we don't really know that the Moebius function counts anything. If we had some kind of proposition that said the Moebius function is the number of ways of doing something, then probably we could prove this without too much difficulty. But right now, the only description that we have of the Moebius function is this strange thing. And so this is actually kind of a, not kind of, this is a quite tricky thing to prove. Okay? And it's interesting that actually at least my favorite proof goes through Moebius inversion. So we're going to kind of turn the tables now. And in the other examples, we first computed the Moebius function, and we used it to formulate a Moebius inversion formula. But what I'm about to do is the opposite. I know the Moebius inversion formula holds. I just don't know what these numbers are. Okay? But I'm going to use an instance of the Moebius inversion formula to compute that number. So how do I do that? Let's say that I have n balls or n vertices, I don't know. Okay? And I'm going to color them with Q colors. So each one gets a color, and that's it. Okay, that's it. The problem is the counting problem is very simple. The colors are numbered 1 up to Q. So how many ways are there to color this thing with Q colors? Just Q to the n. Okay? This is one way of counting this. Okay? But what's another way of counting this? Another way is to say, let me consider which blocks got the same color. Okay? So let me just do an example with n equals 6. So I could say let's say that I want a coloring where maybe these two have the same color and maybe these 3 have the same color and this one has its own color and these colors are different. Okay? In other words, I'm just the way I'm going to do it is that I'm going to choose my balls, put them into different groups, and then each group I'm going to color with a different color. Okay? So what's the number of ways of doing that? Well, first, I should just decide what my blocks are. So that's the same thing as choosing a partition. Okay? And now what are the ways of coloring the blocks? Well, the blocks have to get different colors. So the first block I can give any color to. The second block I can give any color except for the previous one. The third block, any color except for the previous one, and so on, up until the last block. So I just give them different colors. Okay. Let me do something a little bit more general. Suppose that I actually start with a partition already. So I don't start with individual balls, I start with a partition of balls. So these guys are grouped, and these guys are grouped, and these guys are grouped. Maybe this guy is alone. Like that. Okay? And now I want to color with Q colors so that each block gets the same color. Each block is monochromatic. Okay? But now the blocks might get the same colors. Okay? Right? All I'm demanding is that these 3 have the same color, but maybe these 3 have the same color as these also. Doesn't matter. Okay. And let's say that this partition is sigma. Okay, so sigma is a partition of n. Sigma is a partition of the set from 1 up to n. And I want to color the ball with 2 colors so that each block of sigma is monochromatic. So how many ways are there of doing that? Well, it's the same thing. I just have to choose one color for each block of sigma. But I can do the same procedure as before. I can say, well, now a different way of doing this is just to say maybe these 2 blocks are going to get the same color, this one is going to get a different color, and these 2 are going to get the same color. Okay? And so then what I get is the same thing, sum over partitions of the same thing. But what partitions pi can I use here? Partitions that are coarser, right? So I can only use partitions that are greater than or equal to sigma. Okay? Okay, cool. So you see here I have an instance. Here I have exactly the setup of Moebius inversion. I have a function of sigma, which is the sum over things greater than or equal to sigma in the poset of some other function. So I'm thinking of this as f of sigma, and this, sorry, because this is g of sigma, and this is f of pi. Okay? And the other thing, so I mentioned this, that Moebius inversion formula holds both if you have less than or equal to, or if you have greater than or equal to. If you notice, here I have less than or equal, but there I have greater than or equal. But both versions hold, so there's also the dual Moebius inversion formula, where if you're in the situation that this is greater than or equal to t, then the exact same thing holds. There's only one change you have to make, which is that this doesn't make sense anymore because the Moebius function goes from small to big. So all you have to do is switch t. And the proof is the same. I mean, these 2 things are essentially the same formula. Okay, so I have this, and therefore I can now apply dual Moebius inversion. So what does it say? It says that f of sigma, q minus 1 up to q minus size of sigma plus 1 is equal to the sum over pi greater than or equal to sigma of the Moebius function of sigma to pi of now g, so q to the pi. Right? So dual Moebius inversion tells me that this is the case. Okay. So what good is this? It's some formula. If we think about it in the previous paradigm, it's kind of complicated because we already saw these Moebius things are products of the new ends, and they're kind of complicated products. So it's kind of hard to think of this as being a useful formula to compute anything here. But you see the paradigm is very different now because actually this is very simple. This is very simple. We don't really need to compute this anymore. We know what this is. Right? So we're not trying to compute this. We can kind of turn it around and say, well, if this is simple and this is simple, maybe it can help us understand the Moebius function. And in particular, remember that we only care about the Moebius function from 0 to 1. So this is true for any sigma, right? Pi is variable, sigma is anything that you want. So let's plug in sigma to be the bottom element. The bottom element is the partition with all parts singletons. So what do I get? I get q times q minus 1, dot, 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 up until how many blocks do I have? The number of blocks is n. Equals sum pi greater than or equal to sigma mu of 0, comma, pi q to the pi. Okay. So what would I like to do? Well, remember I want this to be 1. I want pi to be 1. So how can I do that? Well, here, these are polynomials in Q, right? This is a polynomial in Q. This is some other polynomial in Q. What happens when pi is equal to 1, to the top element? Then the number of blocks is 1. So I get Q here. And if pi is not 1, then I have more than Q parts, more than one part, and so I get more than 1 Q. So if I compare the coefficients Q, then in the right hand side, I have Q to the 1. And the only thing that has 1 block is the top partition. So I only get mu of 0, 1. Okay? And now you cross your fingers, look in the left hand side. What is the coefficient of Q? I have a factor of Q, and then I have this product. Minus 1, minus 2, until minus 1, which is equal to minus 1 to the and minus 1. So yeah, I like this proof a lot. Actually, I didn't know this proof. I was preparing class and I thought, let me say it a little bit differently. So there is a way of understanding this proof very naturally from the theory of hyperplane arrangements. And I encourage you to think about the geometric meaning of what I just did. But I just realized that actually, even if you haven't studied the geometry of hyperplane arrangements, you can use this argument to give a formula for this Moebius function. And that's great because once you compute it once, you can use it as many times as you want. So, I mean, this was kind of a trivial application of Moebius inversion. What was useful was to use it to get a hold of these coefficients. But now you can turn it around and say, well, now that I actually know these numbers and I know what to plug in here, then I could do other instances of Moebius inversion for the partition lattice. And that turns out to be very useful. Cool. So I hope this gives you a taste of what Moebius inversion looks like. It's really a very, very ubiquitous tool all over mathematics. Do you guys know the word ubiquitous? I didn't know it. Mathematicians use it a lot. Ubiquitous means that it's all over the place. It's a very frequent idea, an idea that keeps coming back, that appears in a lot of places. So this is true with the Moebius inversion and Moebius functions in combinatorics. They're really all over the place. For example, I know that some of you think about Erhard theory, counting lattice points in polytopes, and that's also a very important idea there. Okay. So after having done some examples, I also hope that I managed to convey that if you have a poset, it's an interesting problem and it's not a trivial problem to find the Moebius function. And so here's there's several useful techniques for computing Moebius functions. And the book has many of them, and I want to talk about one that's very important. This is a theorem. People call it Phillip Hall's theorem, which I find kind of strange because usually you just say the last name of the person that proved the theorem. But I guess Phillip Hall is maybe less important than some other Hall, and so Anyway, I guess what that means is that there's another Hall's theorem, which is Hall's marriage theorem, and I assume that this is called Phillip Hall theorem probably is because it's a different Hall. In any case, this is Phillip Hall's theorem, and it says the following thing. Let's say that we have a finite poset. And let P hat be the poset obtained from P by adjoining a bottom and a top element. Okay. Simple thing. An element less than everybody, an element bigger than everybody. And let's say that Ci is the number of chains from 0 to 1 of length I in E hat. So you start with 0 and then okay. So then, so this is enumeration. This is something you can, at least in principle, you could count it. The Moebius function of this hat poset is given by C0 minus C1 plus C2 minus C3. Actually, you know what? I'm finding this formulation kind of strange. Let's just say that P is a finite poset with a 0 and 1. And then you get this. So it's something that applies to any poset with a 0 and a 1. Okay. So that's Phillip Hall's theorem, and let's give a proof. So the proof is gonna go, and again, you could just prove this manually. You could just show that this thing satisfies the recurrence for Moebius numbers. But I think the better proof, the more enlightening proof that explains why this holds, is going through the incidence algebra of the poset. So in the incidence algebra, poset, we had that the Moebius function was the inverse of the zeta function. Okay. Let me remind you how this was. Okay, so you have the poset, and the incidence algebra was the algebra of functions from intervals of the poset to, let's say, the reals. Okay, and this was an algebra where the product was convolution. Remember that if you wanted to know f times g in an interval, then you would look at every intermediate thing, and so f times g of the interval would be f of the lower interval times g of the upper interval, convolution. Okay. So we defined this. The zeta function was the simplest function. Which
I'm stuck on something that may be really silly, but So if we have a finite poset with the bottommost and topmost element, or yeah, how do I know that if I have a chain Cn that I also have a chain Cn minus 1, or that I'm guaranteed that?
I'm not sure that I understand your question. So you're considering a poset that has a bottom element and a top element,
Yeah.
and you're computing, for each length, you're computing the number of chains from the bottom element to the top element. Okay. Now the poset has a certain height, so these chains can only be so long. So you go chains of size 0 minus chains of size 1 plus chains of size 2. But at some point this has to stop because chains can only be so long. We're gonna talk about this in more depth, and I think it will become clearer. Okay, so the zeta function was a very simple function that is 1 for every interval, and remember that that was not the one function. The one function was the function that was 0 for x less than y, and 1 for x equal to y. And our original definition of the Moebius function was that we proved that this was invertible in the incidence algebra, and we defined this to be the inverse. Okay. And now we have been working with the Moebius function in a more kind of manual way, but this was how we defined it. Okay. And then we can do the following thing. This is an algebra, and so we can do this. We can do zeta is 1 plus zeta minus 1. Okay, that's a very simple thing. But the point is that this is kind of like a geometric series. Right? 1 over 1 plus something is equal to 1 minus zeta minus 1 plus zeta minus 1 squared minus zeta minus 1 cubed, etc. Okay. Now, you might worry that this could not be justified because it's an infinite sum, but actually when we were discussing incidence algebra, we already ran into this situation, and what we said is that actually you can check easily that this runs out. So at some point these things start being 0. And actually the reason that that's true is that we showed, and you'll have to go back to your notes to remind yourself of this. Well, actually we can give another argument also. We showed that this is the number of chains of length k from x to y. And the way to prove it is to say, well, sigma is 1 for everybody. Okay. What is sigma to the k? Remember, this is the convolution product, and so what you're supposed to do is start with your interval, and now take k jumps, 1, 2, 3 up to k, and then apply 1 here, 1 here, 1 here, 1 here. You're just multiplying a bunch of 1s. Okay. And so essentially, by definition, this is true. And because this is true, this runs out after some value of k, right? This is a finite poset, so for k big enough, this is going to be 0. Okay, so even though this looks like an infinite sum, it's actually finite. And then you can verify easily that this is the inverse of this. And that's all there is to it, because now if I apply mu of 0, 1, then sigma minus 1 to the k is the number of k chains. And so this is going to be C0, this is going to be C1, this is C2, etc. Okay. So you see this. Yeah. This is essentially a restatement of the fact that mu is the inverse of zeta and the incidence algebra. Okay. So it's some formal manipulation. But we're gonna come to understand this formula a lot better next time. Okay, so, and in particular, right now, maybe it doesn't look like it's a very useful way to compute Moebius numbers, but it turns out that this is one of the most commonly used methods to compute Moebius numbers. And we'll see why next time. Let me just tell you very briefly that the point is that this right-hand side has a topological meaning. This has a topological interpretation. Okay. So what we're gonna do next time is, I mean, we'll take a. I'm not gonna try to teach you all of topology, but I'm going to show you just enough rudiments of topology that that you will understand why this is really a topological formula, and therefore computing Moebius numbers ends up being a topological problem. And then in topology there's a lot of tools, and actually in combinatorial topology there's a lot of combinatorial tools to get to compute topological invariants. I'm sure that sounds kind of mysterious at the moment, and so next time we'll make this a lot more precise.